Cyclohexane is a very interesting molecule. Typically, the way you see cyclohexane drawn is as a flat hexagon. There's a carbon at each vertex of the hexagon, of course, and there are two hydrogens bonded to each carbon at each vertex for a total formula of C6H12. The way cyclohexane is typically drawn makes it look like the molecule is basically planar, right? Makes it look like all 6 carbon atoms are in the same plane defined by the hexagon that I'm highlighting in red. Since we don't see any wedges or dashes, that tends to imply, right, that all of these bonds within the ring are in the same plane as are all 6 of the carbon atoms. This implies, however, that the bond angle between adjacent carbon-carbon bonds is 120 degrees, because we would expect this to be a perfect hexagon, and in a perfect hexagon, the bond angles are 120 degrees. However, we know from our studies of tetrahedral carbon in the past that the bond angle for tetrahedral carbon is 109.5 degrees, not 120 degrees. So something's got to give here. Either the bond angle is not really 120 degrees and the ring is not flat, or the ring is flat but the angle is closer to 120 degrees. Well, in fact, the bond angles are still 109.5 degrees, but the cyclohexane ring is in reality non-planar. In reality, the cyclohexane ring looks much more like a kind of a folded up lawn chair sort of appearance, like this. And so you can imagine, and the way I like to draw it is a little guy kind of lounging on the chair, something like this. Right? You can see how the cyclohexane structure looks a lot like a chair when it's sort of drawn this way. This is an interesting way to draw the cyclohexane structure that shows more of the intricate details of the three-dimensionality of the cyclohexane ring. And in fact, we can add the hydrogens to this structure by adding bonds off of each of the vertices in this chair drawing. And I'll do that briefly here, and we'll talk in more detail about how this works here shortly. One thing we can notice right away is that there are kind of two different types of bonds in this structure. There are these bonds going straight up and down, like this, and there are bonds kind of going out to the side, like the ones I'm highlighting here. We'll come back to that point in a second. So how do we actually draw these cyclohexane chairs quickly and reliably? That's going to be important, especially as we look at multiple cyclohexane conformers. The easiest way to do this, in my opinion, is to use what's called the parallel lines method. The parallel lines method relies on the fact that if you pay very close attention to the orientation of bonds within the chair, we see various bonds that are parallel to each other in this projection. So for example, the two I've highlighted here are parallel, and even some of the bonds out to the side, such as this bond and this bond, appear to be parallel to each other. So the entire drawing method, with the exception of these bonds pointing straight up and down, which are easy enough to draw on their own, is driven by the fact that bonds are parallel to each other in this projection. So to get started, first of all, we can notice that there are sort of two ways we can draw a chair. We can draw it slanting to the right or to the left. And I'll draw down here a chair slanting to the right, starting with two sets of parallel lines that are slanting to the right. We could also, if we wanted to draw a leftward slanting chair, start with two bonds that are slanting to the left, like so. These two bonds that we start with, here and here, are eventually going to become the bonds on the far right and the far left of the final structure. From here, once we've got those down, we draw a second set of parallel lines, which I'll highlight in a different color for us. And notice that when I draw these, I'm drawing approximately a 120 to 109.5 degree bond angle there. Kind of a shallow, obtuse bond angle, but the lines are still parallel to each other. At this point, we've got all 6 carbons implied. Notice that each arrow-like shape implies 3 carbons, and we just need to connect the carbons that we haven't yet connected with a third set of lines that, by construction, will be parallel to one another, here and here. Notice that those lines are parallel to each other, and that happens by construction because we've taken 2 sets of parallel lines and used 2 of the same angle. At this point, we've generated the chair skeleton for the 6 carbons. We did it, recall, using 3 sets of parallel lines. set 1, the black set, on the left and right, set 2, which is the blue set kind of on the top and bottom, and then set 3, the red set, which simply connected the carbons that were left unconnected after we had laid down the blue and black sets. Where I like to go from here is drawing the bonds that are straight up and down. And to decide how to do this, we can pay attention to each of the vertices and kind of the direction that the point is pointing at each vertex. So for example, for this vertex in the upper right here, notice that the point is kind of pointing up. If we look at the two bonds that are heading into that carbon, here and here, they kind of form a point that's pointing upwards. And so the bond here that's either straight up or down is in fact straight up. We'll see also why this makes a lot of sense when we draw in the remaining bonds in a second. So backing up a bit, we're going to draw this straight up, and then once you've got one down, the bonds that are straight up and down alternate. Up, down, up, down, up, and here in the back, down, and for a little extra artistic flair, I like to draw that bond actually behind the bond in the front, just to show a little bit of three-dimensionality in the structure. Now we need to add in these bonds pointing out to the side, and we can do that by looking at the carbon where we want to add the bond and going 2 bonds over and drawing the bond out to the side parallel to the bond that's 2 bonds away. So in other words, at this carbon I've highlighted in green, the blue bonds are 2 bonds away from this carbon, and so the bond out to the side here will be parallel to those 2 bonds, roughly. Let me do a little bit better job of drawing that. So we can see then that the newly drawn green bond is parallel to both of the blue bonds that are 2 bonds away. So we can continue doing this for the other carbons. Here we're parallel to the red bonds, and so we draw a bond in this direction. Here we're parallel to the black bonds, and when we get back over here, we're now again parallel to the blue bonds, and so we go in this direction. Now we're parallel to the reds again and go in that direction. And finally, there's one more parallel to the black bonds in that direction. And these are, as you may have guessed, in the parent cyclohexane, these are where the hydrogens are located. And as you may have also guessed by now, what we call these 2 sets of positions, the positions in black, which are pointing straight up and down, are called axial, while the positions in green, which are sort of pointing out to the side, are known as equatorial positions. And just to show you briefly how this would work for the leftward slanting chair, we can apply the exact same process. We've got 2 of the parallel lines down, we do kind of a 120 degree or so bond angle here, and then we connect the carbons that are currently unconnected to generate the last set of lines, and this is our leftward slanting chair. And again, the same idea for drawing the axial positions applies. Go kind of in the direction that the point is pointing on one of the carbons. Usually I start on one of the either far left or far right carbons and then alternate as we move along to generate those axial positions. To generate the equatorial positions, draw lines that are parallel to the bond 2 bonds away. So parallel to the blue, to the red, to the black, blue, red, and black. And there we have it.